in continuation to the hot dipping operation, in part 2 we will discuss about hot dip galvanizing process, that is specifically the hot dipping of zinc and its alloys. So, as I mentioned you that hot dipping of zinc is very important, and particularly for zinc deposition among most of the parallel techniques, 75% of the industries they do look for coating by hot dipping technique. So, because of the biggest advantage of having the completely dense pore free coating and very strong interface. Now, if you talk about, and also very thick deposited layer. Now, if you talk about the zinc coating thickness which is desired, you will find that because of its application or application requirement, or maybe the requirement of its service in corrosive environment, thicker the coating, better is it, better is the service life. So, service life changes from 5 years to as high as 80 years depending on the thickness. So, you will find that thickness is around 3, if you go on increasing the thickness from 0.25 mils to 3 mils, the or maybe you can say that 10 micron to 120 micron, 130 micron, the service life increases from 0 hour, or maybe you can say that 1 year to as high as 80 years. So, thickness of zinc is very important. So, that apart from the all the parallel techniques which are available for zinc deposition, you will find that hot dip galvanizing offers the maximum thickness on the surface with strong interface. And apart from that, you will find spray deposition technique also offers very high thickness, but in spray deposition technique the interface is not really so strong as in hot dipping, and also there are few porosities or defects on the surface. So, usually it is observed that hot dipping is preferred to spraying process for zinc deposition, where you are looking for very large service life of the component. Now, if you talk about the service life of component, you will find that it certainly depends on the environment. So, in the rural environment where there is not much pollution, you will find that not much humidity, you will find that service life is higher than that of marine environment, than that of high temperature marine environment, than that of normal suburban and then industrial environment. In industrial environment, you get minimum lifetime because of presence of lot of porosities in the environment, because of presence of lot of different impurities in the environment, and also different particles which are present in the environment, and lot of carbon soot, sulfur dioxide, these all particles are also present in the environment. So, those particles basically they get deposited onto the surface, different materials, and when they are deposited on the surface, naturally the absorptivity of the surface increases. So, we will find that surface will be more prone to absorb the moisture from the environment than that of the typical rural environment, where there is not many impurities in the environment. So, as a result of which you will find that in industrial environment the service life of the component by corrosion is much lower than that of the same in rural environment. So, you will find that the service life is basically the relative term, it depends on the environment where the component is used. But whatever the environment may be, as you go on increasing the thickness of the zinc coating, you increase the service life to a large extent. So, as I mentioned you, among these all parallel techniques, hot dipping offers the maximum thickness with a strong interface, and apart from that the metallizing or thermal spraying route also offers a similar level of thickness, but in spraying technique the interface is not really so strong as in hot dipping. At the interface there is always mechanical interlocking, or maybe the interface is basically not there is no interdiffusion layer at the interface, but mechanism of bonding is interlocking, mechanical interlocking, and lot of porosities and defects are there in the coated layer. when you develop it by thermal spray deposition technique, but you get similar level of thickness, but surface is also quite rough. When you talk about other parallel techniques, those are like painting technique. In painting you can have the zinc dispersed zinc as dispersed particles. So, there you will find that paint layer again gives the very poor interfacial bonding, but thickness is also very low, not really so high as in hot dipping, and also there are a lot of defects in the paint layer. Then finally, galvanized sheet, if you see galvanized sheet is also galvanizing is also mechanical or maybe you can say that mechanical cladding is also another way of zinc coating. So, where you basically take zinc sheet and steel sheet together and then go on cladding it over each other by application of mechanical force. There is always thickness limitation, because if it is too thick then there will be problem of non-uniformity. So, thickness is limited and interface is also very strong, but as strong as this thermal spray deposition, it's not really so strong as in hot dip galvanizing. Now, another parallel route by which you can do zinc coating is by electro deposition process. So, here the thickness is of major trouble. You cannot go beyond certain thickness, maybe 20 to 25 micron is the maximum thickness that you can achieve when you go for electro deposition, and interface is also not so strong. So, if you talk about different parallel techniques, you will find that so many techniques are available. So, depending on the applications, you have to look for the technique which you should opt for. So, when you are looking for the zinc coating for mild environment where the component shape is very much complicated in nature, and you are interested to have very nice polishing, fine polishing on the surface, you go for electro deposition. When you talk about the galvanizing for utilities and furniture purpose, there you can go for this clad bonding operation. In long structures like bridges, you can go for painting operation or thermal spraying operation. In badge component where dimension is also not so big, but medium size dimension, you can go for hot dipping operation by continuous processing. So, depending on the applications where you are looking for the coating, you can choose different coating techniques, but it is important that you choose proper coating technique and proper parameters to have the desired result in the coated product or desired properties of the coated product. Now, if you talk about hot dip galvanizing, then you will find, as we mentioned you in the other case, here also the surface finishing is the or surface cleaning is the mandatory step which you should follow prior to hot dip galvanizing. So, what you do is that you basically go for several steps of cleaning, like when there are dirt particles or dust on the surface, you go for caustic cleaning and then rinsing, and if you have then lot of oxide layer on the surface, you should go for pickling operation. So, in pickling you basically take 3 to 5% hydrochloric acid solution and temperature is 35 to 40 degrees Celsius. So, you dip the component in the pickle reagent for 1 minute to 2 minute maximum, and then you take it out and then go for rinsing operation, and then your surface is cleaned. And prior to hot dipping, you can go for flux solution dipping, so that your surface is no more oxidized prior to your zinc coating. Then go for drying operation, then go for zinc coating, and then you go for cooling and inspection and dispatch the component. So, these are the steps which are followed, and this is a kind of batch processing, and you can also make it continuous processing by typical having this kind of arrangement where you have the cleaning section, direct fire section, and hot dipping section and withdrawer section, they are kept one after another. So, what you do is that In cleaning section, you basically clean it by different techniques like solvent cleaning or pickling or drying, these all techniques, and then you can go for fluxing operation, and then you go for hot dipping, and then finally by jet finishing nozzle you just go on finishing and monitor the thickness, and then you can go for galvanizing operation in the furnace. So, this is the hot dip galvanizing process, that continuous processing. So, now one of the biggest advantage of the hot dipping is that that in hot dipping you get completely dense coating. It is not, you do not really get many defects on the surface of the coating, except the spangle formations and different designing is there, and microstructural segregation. So, apart from those techniques, apparently those defects, apparently there is not many significant defects observed in the hot dipped coating actually. So, it is very interesting way of depositing on the surface of metallic materials, which can offer very good corrosion resistance property. But one of the biggest disadvantage is that the interface, though interface is strong, but if you see the interface carefully, you will find that at the interface there are several intermetallic layer formation. So, those intermetallics are highly brittle in nature. So, that brittleness of the intermetallic in the iron zinc system creates problem for applications, for its applications. If it is pure iron zinc, pure zinc coating if you talk about. So, you will find that if you just quickly go through the iron zinc interface, you will find that at the interface there are this is a zinc rich corner, because usually when you dip the iron rich component or iron based component in molten zinc, usually there is dissolution of iron from the surface, and that dissolved iron basically mixes with zinc and then forms different intermetallics. So, you have to see the phase diagram from the zinc rich side. So, you find that from the iron rich side there are different intermetallics which might form like gamma 1, gamma 2, that then delta phase, zeta phase, and then pure zinc onto the top with iron in solution. So, these are the different intermetallics which can form at the interface, starting from the interface actually. So, these all intermetallics are not yet I mean they are very much brittle in nature, most of the intermetallics. So, when you keep the iron zinc zinc coated particularly galvanized component in the normal environment, you will find that there is formation of fine cracks after a long time. So, these cracks are because of these all different intermetallics as I mentioned you, which are formed, and if you just quickly go through the intermetallics, you will find that they are having the typical SCP structure, monoclinic structure, FCC, BCC structures. Even though there are BCC structures, but they are also not really so ductile as is normal FCC. So, these all phases form one after another, and these all phases, because of formation of these all phases, you will find that when you keep the galvanized steel for long time in normal environment, there is formation of fine cracks starting from the interface towards the surface. So, fine cracks are not good because it basically creates a path for the transportation of water molecules from the environment, but still it is acceptable as because of the fact that zinc also saves the surface by the process of the sacrificial action. So, even though there are possibilities of formation of lot of intermetallics at the interface and which are brittle in nature, the presence of whom actually creates trouble, because the presence of whom actually can cause crack formation at the interface, but still as it is zinc coating, it is acceptable because zinc coating offers the sacrificial action to save the underlying substrate. So, even though there is that these all cracks formation on the at the interface, but still you will find that as zinc is there on the surface. So, zinc basically preferentially corrodes, and by that process the steel is saved, underlying steel is saved. But again even though that is there, but still you find that the overall lifetime of the component gets reduced. So, whatever the fact may be, even though the steel substrate is saved, but still you cannot really allow this kind of degradation to occur, or maybe you cannot allow these kind of defects to form at the interface, because it deteriorates the overall service life of the component. So, when you talk about reducing this particular, when you talk about that saving the component by proper way, what you go for is that you have to look for typical different ways to combat this kind of intermetallic formation. Usually people go for alloying with aluminum, they do go for alloying with different other metals as well, in order to reduce the kinetics of the iron zinc intermetallic formation. They also go for annealing operation to homogenize the microstructure. So, now this is the slide which shows you the schematic of the intermetallic formation with time. So, when time is very short, then if you just keep iron in zinc molten zinc, you will find there is no intermetallic, but gradually there is formation of intermetallic, and the first intermetallic which forms is basically eta phase, and then as you go on increasing the time, you will find that there is delta phase formation, zeta transforms to zeta prime or zeta 1 phase, and then gradually there is formation of zeta 1 and zeta 2 and gamma phase also at the interface. So, finally, you will find the gamma phase at the interface, followed by which there is delta phase, then zeta 2, zeta 1, and then finally zinc with iron in solution and pure zinc. So, these are the different intermetallic phase formation sequence when you dip the iron based alloy into the molten zinc. So, if you see the kinetics of the different phase formation, you will find that they are having different kinetics, like for example, if you talk about gamma phase kinetics, so this is actually it is slowest. So, you will find that gamma phase forms at a much slower rate than that of the delta phase and that of the zeta phase. So, if you see the then from the layer growth itself, you can say that gamma phase kinetics is quite less. So, it is there at the interface, but zeta and delta phase formation kinetics is quite high. So, they form at a much faster rate. So, the kinetics of different phase formation is also equally important, they are having different T values. So, if you are interested to get rid of the intermetallics, as I mentioned you have to add some ternary elements into the molten zinc bath. So, usually aluminum is a very popular ternary element which is added in the molten zinc in order to reduce the kinetics of this intermetallic formation. So, if you add aluminum, naturally it serves several purposes. First of all, aluminum improves the oxidation resistance of this bath. Second purpose which is served is that there is formation of iron aluminum intermetallic at the interface, as a result of which the zinc cannot form any kind of intermetallic with iron. So, it prevents the formation of iron zinc intermetallics by forming a very thin layer of iron aluminide on the surface. And third purpose which it solves is that it promotes that typical it increases the luster of the coating actually. So, because aluminum, whenever you add aluminum, you will find that coating is highly lustrous. So, usually in zinc bath very low percentage of aluminum up to 1% is added, which basically serves these all purposes. So, you will find that the iron zinc intermetallic formation kinetics is reduced. But apart from 1% aluminum, there are also two more aluminum percentage which are added in the zinc bath by changing the composition itself. One is 5% aluminum, another one is 55% aluminum, which are called galfan bath and galvalume bath. So, in the case where you have normal galvanizing with 0.1% aluminum, you will find that intermetallic formation is partly reduced, you will find on the surface there is zinc coating, and at the interface there is Fe2L5 phase, and the thick monolithic intermetallic formation is reduced. So, for example, this is the case of 0.2% aluminum percentage galvanized coated microstructure. Here you will find that at the interface there is Fe2L5 phase formation. So, this phase actually, as I mentioned you, it reduces the kinetics of Fe zinc intermetallic formation, but as the aluminum content is quite less, you will find that if you do not really control the time carefully, you will see that there is the failure of the coating in a very large extent basically. So, it is called outburst formation. So, outburst formation is one of the biggest trouble associated with iron zinc, associated with the galvanizing, where you have very low percentage of aluminum. So, aluminum percentage is quite low, so 0.2%. So, if time is very less, there is no problem, there is Fe2L5 phase formation, on top of that there is molten zinc actually with iron in solution. But if your time is quite high, what happens is that because of large time which is available, there is that molten metal diffusion through the intercolumnar porosities of the Fe2L5 layer, and that molten zinc actually can go inside the iron through grain boundaries, and then creates presence of, or maybe it forms different types of intermetallics at the grain boundary regions. So, you will find that there is local change in the concentration of the zinc, as a result of which local formation of iron zinc intermetallics. That iron zinc intermetallics creates trouble because it applies pressure, and as a result of which after a while there is over breakage of the Fe2L5 layer, which is called outburst formation. So, outburst formation is never desired, because not only it basically breaks the Fe2L5 layer, but it can also apply such a high pressure that your coating can also fall out. So, this is the typical mechanism of outburst formation which is shown here. So, usually if aluminum percentage is quite low, like 0.5%, if you dip it for 0.5 minutes, for example, when there is no chance of diffusion of the zinc, there is no trouble. But if you allow more time, what would happen is that zinc will go on diffusing through the grain boundaries of the iron aluminide interface, and which grain boundaries actually match with the grain boundaries in alpha or maybe alpha phase. So, what happens is that this particular zinc gets diffused in, and when it diffused in through the grain boundaries, naturally there is always chemical potential difference along the grain boundaries and between the grain boundaries and inside grain, as a result of which zinc again goes on diffusing from grain boundary to the grains, and there is intermetallic, wherever there is diffusion of zinc, it reacts with iron and there is iron zinc intermetallic formation. So, intermetallic formations are there at the interface over there, as well as intermetallic formations are there along the grain boundaries. So, gradually there will be highly applied pressure on the grain boundary regions, and this particular intermetallic grows on the surface. So, after a while you will find that it applies lot of pressure. So, when you just go on taking it out, you will find that the zinc coating basically falls out. So, you have to be very much careful and control the time carefully, so that there is no chance of outburst formation. Otherwise, you apply some more aluminum in the coated layer, so that there is no possibility of the outburst formation at the surface. So, in order to prevent that outburst formation, or maybe in order to improve the quality of the zinc coating further, galvanized coating further, you can have two more solution. One is galvan coating, where you add 5% aluminum in the coated layer. So, when you use 5% aluminum in zinc, that is typical eutectic composition. So, what happens is that there is typical eutectic columns of iron and aluminum and zinc formation. So, you will find that as aluminum percentage is quite high, the outburst formation time can be increased, or maybe threshold time for outburst formation start can be enhanced. So, you have enough time for the galvanizing to do, and on the other hand another advantage of this galvan coating is that in the microstructure you will get typical eutectic microstructure which offers higher strength. So, in this kind of coating you get a bit superior strength, you get good corrosion resistance property. In addition to that, you avoid the formation of the outburst, because here aluminum percentage is very high. So, at this aluminum percentage, if you are interested to form that outburst, naturally you have to wait for some more time. But one of the biggest advantage of this hot dip galvaning is that or maybe where you use galvan as a bath or 5% aluminum as the bath, there is dent formation at the interface basically. So, this is because of the fact that when you go on solidifying it, that at the middle layer there is still liquid, because it is a eutectic composition. So, temperature is quite low. So, if you think of solidification process, you will find that all other layers solidifies, but last layer where it is still in liquid state, it gets contracted because of solidification shrinkage, and there will be formation of the typical dent mark on the in the middle of the galvan coated component. So, there you have to put some extra liquid, so that this problem is probability of this dent formation can be minimized. So, another coating composition in galvalume where you use 55% aluminum. So, as you are using 55% of aluminum, it is always better. This is typical hypereutectic composition. So, you will find typical primary dendrites of the typical aluminum in aluminum zinc intermetallics, but here you have to add a little bit of silicon, because if you do not add silicon, then naturally the fluidity of the bath will be quite low. So, usually 1 to 2% silicon is added. So, if you add this silicon, naturally fluidity increases, but on the other hand there is also that silicon whisker formation at the interface. So, this problem is always there, but it is to some extent beneficial, because when you have these whiskers of tin, naturally whiskers of silicon, naturally it can also improve the strength of the bond strength of the coating to a large extent. And from that whisker itself there is microstructure development when you do solidification processing, when it is solidified actually, and at the interface there is a Fe2L5 layer formation which is actually quite thick, and the possibility of outbursting is also minimized. So, as I mentioned you that these are the 3 important ways by which you do galvanizing process, and each and every step is having each and every process or bath is having its own advantages and disadvantages, and also there is a lot of cost associated with aluminum addition. So, if you add aluminum to a large extent, the temperature of operation goes high, and that is also the bath, also maintenance of the fluidity of the bath can have the you have to take proper precaution to do that. These all problems are always there, but again some of the advantages you get which is not possible to achieve by the single step normal single galvanizing process. So, another way of typical reducing the possibility of the stress which are possibility of the relieving the stress, or maybe minimizing the possibility of the this brittle hedge formation is by galvanizing operation. So, galvanizing operation is nothing but after galvanizing you go for typical annealing operation. So, there are 3 types of galvanizing process. One is type 0, which is applied for underalloyed coating containing predominantly zeta phase, where time is quite less. So, where you do not get any other phase, but only zeta phase. And type 1 galvanizing, which you apply for those cases where optimum alloy coating is there less than 1 micron interfacial gamma layer and an overlaid coating of delta phase interdispersed with small amount of zeta phase, an overalloy coating which you have very thick gamma layer and an overlay coating containing delta phase and basal plane cracks perpendicular to the coating substrate interface. So, in all coating, in all galvannealing, you will find that this is type 0 galvanizing, type 1 galvanizing and type 2 galvanizing. So, here you will find that in all cases what you do is that you basically change the time of the annealing operation. So, time of galvannealing is temperature of galvannealing usually from 600 to 650 degrees Celsius, and depending on the alloy which you are using, your time also changes. So, with optimum timing you can have the typical base microstructure which is consisting of for example, at the end of the galvannealing you can have the microstructure containing zeta phase on the top, then delta phase in the middle and the interfacial layer, very thin interfacial layer. So, this is nothing but typical annealing operation to homogenize the microstructure and also to release the stress which is developed in the galvannealing process, which is developed by galvanizing process. Now, if you talk about the typical corrosion rate or maybe lifetime of different coated product, you will find that by addition of the aluminum, your corrosion loss, average corrosion loss is reduced to a large extent. So, aluminum addition is very good because it not only reduces the possibility of the intermetallic formation at the interface, but it also reduces the possibility of typical it also reduces the possibility of reduces the corrosion loss to a large extent. So, it is very important that you do add aluminum and you apply galvan bath where your service environment is quite hectic in terms of the environmental species like severe marine environment or in marine environment. So, in brief we can say that in this particular talk we discussed about the hot dip galvanizing process and its importance, particularly the importance of using different baths in hot dipping operation like galvan and galvalume bath, and also the galvannealing operation which is very important, and still research work is going on to minimize the typical intermetallic formation by addition of different ternary element like aluminum, silicon, copper, titanium. So, effect of those elements are also being studied to a large extent, and finally, you do optimize the process parameters for galvannealing operation. So, that you get the desired result, you get the desired homogeneous microstructure with minimum stress level in the coated product. Thank you very much.